Welcome to the Explainer. Today, we're going to unpack one of the absolute coolest, kind of hidden superpowers in the world of chemistry, electrolysis. Have you ever actually wondered how someone magically plates a cheap metal spoon in pure silver? Or, how we refine the copper that's literally powering all the electronics in our modern world right now? Well, it all comes down to this invisible dance of chemical forces and electric currents. In this explainer, we're mapping out exactly how this whole process works, breaking it down structurally so you can actually visualize the science happening right in front of you. Okay, let's dive into this. Here's our agenda for today. We'll start with the basics of electrolysis, then we'll look inside the electrolytic cell, cover the rules of attraction, check out some real-world electrolysis examples, and wrap up with practical applications of electrolysis. Section 1. The basics of electrolysis. Defining the terms. Let's lay out our foundational vocabulary. So electrolysis is basically the decomposition of a chemical compound, specifically we call that an electrolyte, in either an aqueous liquid state or a fused molten state, just by passing a direct electric current through it. The result? The discharge of ions as neutral atoms. But what you really need to take away from this is that it fundamentally involves a chemical change. It's a redox reaction, meaning it's got both oxidation, that's the loss of electrons, and reduction, the gain of electrons. But obviously, for any of this to even happen, we absolutely need the right kind of compound. And that brings us to a really stark contrast: electrolytes versus non-electrolytes. Electrolytes are your ionic compounds, things like sodium chloride or copper sulfate, that actively conduct electricity and undergo that chemical decomposition we just talked about. On the flip side, non-electrolytes are covalent compounds. Think of everyday stuff, right? Pure water, alcohol, or just a simple sugar solution. I mean, if you stir sugar into water and try to pass a current through it, absolutely nothing happens. It's not going to conduct or decompose. But dissolve salt in water, boom. Suddenly you've got a highly conductive electrolyte that's totally ready for our invisible chemical dance. Moving right along to section 2, inside the electrolytic cell, meet the actors. Now that we've got our terms down, let's actually set up the physical stage where this reaction takes place. Think of it as our chemical dance floor. And this brilliantly illustrates the setup. We've got a non-conducting vessel holding our liquid electrolyte. Dipped right into this liquid are two electrodes, and they're connected via a metal wire, a switch or key, and a bulb, looping straight back to a battery. The battery is what provides that crucial direct electric current. Once that switch is flipped on, the electricity flows and the chemical decomposition officially starts. Plus, that little bulb, it actually acts as an indicator. A bright glow tells us we have a strong electrolyte, while a dim glow means it's a weak one. But honestly, the real stars of this stage are the two electrodes, the anode and the cathode. And here are the basic rules of the dance floor. Opposites attract. The anode is connected to the positive terminal of the battery. So because it's positive, it naturally attracts the negatively charged ions, which are called anions. When those anions hit the anode, they drop their excess electrons, a process we call oxidation. On the flip side, the cathode is connected to the negative terminal, so it acts like a giant magnet for the positively charged ions, the cations. And once those cations reach the cathode, they gain electrons, which is our reduction. Section 3. The rules of attraction. Selective discharge. So what happens when you have multiple different ions crowded into our electrolyte, all competing on this dance floor? Well, we call this selective or preferential discharge. When a bunch of ions are present, they don't all just discharge at once, right? They kind of have to wait their turn based on three main factors. First, there's their relative position in something called the electrochemical series. Second, the concentration of the ions in the electrolyte. Basically, higher concentrations mean a much higher probability of being discharged. And third, the actual nature of the electrode itself, whether it's just an inert spectator letting the current pass or an active participant getting involved in the reaction. Let's take a closer look at that first factor, the electrochemical series. Notice the order here. Right at the top, you've got highly active metals like potassium and calcium. Now, these guys ionize incredibly easily, which means they're super stubborn about discharging. They discharge with the absolute most difficulty. But as you travel down the series to metals like copper and silver, they hold on to their ionized state a lot more loosely. They gain electrons back and discharge with a ton of ease. And the exact same rule applies to the negative anions on the right side. The lower their position in the series, the greater the tendency they have to be discharged at the electrode. Section 4. Real-world electrolysis examples. Watching the reaction. Okay, it's time to shift from theory to practice. Now, what's really interesting about this specific physical setup is the actual requirement for our electrolyte, lead bromide. See, in its solid state, lead bromide is completely a non-conductor. To free up its ions so they can move and carry a current, we literally have to melt it. That's exactly why there's a heat source right beneath that special silica crucible. We use silica because, well, it's non-reactive, and it can handle the extreme heat needed. We're talking over 380 degrees Celsius, without cracking or conducting any electricity itself. Inside, we use graphite electrodes because they're inert. They won't react at all with the volatile products being formed. So, what's actually happening inside that superheated crucible? First, the intense heat dissociates the molten lead bromide into positive lead ions and negative bromide ions, following those rules of attraction we talked about. The positive lead ions migrate straight to the negative cathode. There, they gain 2 electrons and discharge, leaving behind this really beautiful silvery green deposit of pure lead metal. Meanwhile, the negative bromide ions are migrating over to the positive anode, where they lose electrons. They pair up into molecules and then evolve into these striking reddish-brown fumes of bromine vapor. It's quite a sight. Let's look at another classic example, the electrolysis of water. As we established earlier, pure water is practically a non-electrolyte. I mean, it consists almost entirely of molecules, not free ions. So to make this work, we actually have to acidify the water, usually by adding just a few traces of dilute sulfuric acid. That acid is a game changer. It helps dissociate the water into positive hydrogen ions and negative hydroxy ions, which greatly enhances the overall conductivity. That way, the electric current from our battery can finally do its thing through the platinum electrodes. And when that current starts flowing, we see something incredibly consistent happening at the electrodes, a strict 2-to-1 ratio. For every 2 molecules of water that get decomposed, exactly 2 volumes of hydrogen gas are liberated at the negative cathode, and exactly 1 volume of oxygen gas is evolved at the positive anode. It's literally a perfect mathematical demonstration of water's molecular formula, H2O, visually separating right before our very eyes. How cool is that? Section 5. Practical applications of electrolysis. Real-world superpowers. This is where we finally see how these microscopic rules fuel some major macro-level superpowers. I really want you to think about this question. We've talked all about ions migrating and metals depositing, so how do we use this exact same process to turn a cheap everyday metal spoon into an expensive-looking piece of silver cutlery? Let's move to and see how this builds into the process known as electroplating. Here, we've got setups for both nickel and silver plating. The core mechanics, they're completely identical to what we've just been learning. The cheap article that we want to plate, let's just say it's an iron spoon, is always placed at the negative cathode. The pure metal we want to coat it with, like a solid block of pure silver, goes at the positive anode. In this particular setup, we have an active electrode. That pure silver anode is continuously dissolving into the electrolyte solution as ions, migrating completely across the bath and firmly depositing themselves right onto the spoon at the cathode. But for electroplating to actually look good, the whole thing has to be super carefully controlled. The base article is always the cathode, and the plating metal is always the anode. Plus, the electrolyte has to contain ions of that plating metal. But look at point number 4. This is absolutely crucial. You must use a low current for a longer period of time. If you get impatient and use a high current, the metal deposits way too fast, and you end up with this uneven, messy, brittle coating. A slow, low direct current is what ensures a smooth, firm, and highly uniform, lasting deposit. So, the crucial point is that this highly controlled migration of metal from one side of the bath to the other isn't just for making things look pretty. We also use it for electrorefining, which is essentially purification. Here you see the refining of copper. At the anode, we place a massive, thick block of impure raw copper. And at the cathode, a paper-thin sheet of 100% pure copper. When the current runs, the copper at the anode dissolves and migrates, literally plating pure copper onto the cathode and building it up into a thick, highly valuable block. But wait, what actually happens to all the impurities in that raw block? Honestly, this is one of my favorite details in this entire explainer. Just read this quote. The impure block of copper gets used up, and the impurities settle down as anode mud or slime, which contains insoluble impurities like gold and silver. Yeah, you heard that right. By purifying the copper, the process neatly filters out all the dirt and zinc, but it also drops precious metals straight down to the bottom of the tank. Extracting that mud actually yields bonus materials like solid gold and silver. It's like finding hidden treasure in the sludge. And that brings us to the end of our structural journey through electrolysis. We've seen how opposite charges literally pull metallic elements apart and perfectly stitch them back together, transferring matter completely invisibly across a liquid bath. I really hope this helps you see the everyday items around you just a little bit differently now. Next time you pick up a piece of silver-plated cutlery, or even just power on a device relying on refined copper, ask yourself, what invisible chemical dance made this possible? Keep learning, and I'll catch you in the next explainer.